Morning, welcome to
FamilyMath101.
FamilyMath number 101. What number would that be if that was in binary?
5.
5?
Yeah.
Cool. Binary is fun, isn't it?
Yeah.
Alright, today we're going to talk about Fermat's last theorem. And I think I'd like to introduce it by talking about the Pythagorean Theorem, which says in a right triangle, if this is A, this is B, and this is side C. What's this side called in a right triangle?
The hypotenuse.
The hypotenuse. Do you know what the Pythagorean theorem says?
A squared plus B squared equals C squared.
Very good. A squared plus B squared equals C squared. And we have all sorts of fun little triangles, like what's a famous Pythagorean triangle with integers?
3, 4, 5.
So we could have a triangle that was 3, 4, and 5. Did you know about that one?
Don't think so.
Don't think so? Okay, well there's also, I could just multiply all these by 2 and I could get 6, 8, 10. That's another one.
Or 300, 400, and 500.
Yeah, or 300, 400, 500. But there's other ones too. There's 5, 12, 13. So we could check that. What's 5 squared?
25.
25. Do you know what 12 squared is?
144.
Very good. Do you know what 13 squared is?
169.
So let's see, does 25 plus 144 equal 169? Whoops, 169.
So
Well,
let's see.
let your brother do it. What's 25 plus 144?
Well, it's 25 plus 140. It's 165 plus 469.
Hey, high five. Look at that. So we got a 5, 12, 13. There's an 8, 15, 17. So there's lots of numbers that work for this. But in the 1600s, I think it was 1637, but let's say in the 1600s because I'm not exactly sure when, this mathematician Fermat said if you take a higher n, a to the n plus b to the n equals c to the n for n, an integer greater than 2. So not the Pythagorean theorem, but so something like 3 cubed plus 4 cubed equals 5 cubed. He said there's no solutions to this for any n bigger than 2. None. So no solutions at all. And you know what he said?
What?
He was writing a book and he said, well, I know how to prove this, but I don't have enough room on this page in the book to prove it. So just believe me, it's true. That's what he said. And you know what?
What?
No one could prove it. Nobody could prove it. So this was in the 1600s, 1637, and you know when someone finally proved this was true? That there were no solutions, no numbers ever satisfied this if the power was bigger than 2?
When?
In 1995. And it was a mathematician at Princeton named Andrew Wiles. Princeton's in New Jersey. Have you ever heard of Princeton before?
No. Yeah, I have.
You have? Okay. Have you ever heard of 1995 before? Was that a long time ago?
Yeah. It's 2013 now.
Yeah, it's a pretty long time ago. Do you think they had iPhones then?
Probably. But
Probably.
they weren't iPhone 5s.
No, they didn't have iPhone 5s then. Definitely not. You think they had cars then?
Yeah. Maybe.
Maybe. Maybe those ones that you had to push with your feet, like in the Flintstones. So anyway, so Andrew Wiles proved this in 1995, and then there's a TV show called The Simpsons. Have you ever heard of The Simpsons?
Yes.
They like to play jokes sometimes. So on 2 of their episodes, they've written these equations in their episodes: 3,987 to the 12th plus 4,365 to the 12th equals 4,472 to the 12th. And they've written another one, 1782 to the 12th plus 1841 to the 12th equals 1922 to the 12th. And you know what? If you check them on like a calculator, on like a handheld calculator, like on your iPhone,
Yeah.
it looks like these work. But they can't work, right? Because they proved, Fermat conjectured and then Andrew Wiles proved that you could never have solutions like this. So who do you think is right about this math? Like one of the greatest mathematicians who ever lived, or the Simpsons?
Always the greatest mathematician.
What do you think?
Don't know.
Don't know, it might be a tie?
Maybe.
Okay, well let's try to look at what I did is I actually made these numbers, and they're huge. They're like So they're so big you can't even try to understand them, really?
We don't have enough space to write them.
Yeah, it's funny. We can prove it, but we don't have enough space on the board, right? Ha ha! So let's look at this one here, because you guys can see that this equation is not true. Okay? Now, do you know your 12th powers of 1,841?
No, I don't think so.
What? Didn't I tell you to memorize all those 12 powers?
I don't think so, but
Well, you have a calculator.
Oh, I do have a calculator, that's right.
We could use our handy dandy last digit.
Ah, we could do our last digit trick, or we could do something even simpler. Is this an even number or an odd number?
It's even.
Even. And what do you think powers of an even number are going to be? Are they even or odd?
Probably even.
Even. Powers of even numbers are even, because you're all taking an even number times an even number, right?
Yes.
What about this number?
You have this one's odd.
Okay, what about powers of an odd number?
Well, even powers of an odd number.
What about powers of an odd number? What does it mean? What does this to the 12th mean? Can you tell me? What does it mean?
It's 1841 times 1841 12 times.
Right, 1841 times 1841 times 1841. So we're taking 1841 times itself. Is that going to be even or odd?
Well, we're just doing odd times odd times odd times odd times odd.
That's right. We're just doing odd times odd times odd times odd times odd times odd times odd 12 times, right? And so is that even or odd?
Well, I think it's even.
You do?
Well, I think it's actually, yeah, because it ends in a 1.
So odd times odd is,
It's even. Wait. Well,
think about 3 times 3. 3 times 3 is,
9. Odd times odd is odd.
odd times odd is odd, and odd times odd 12 times is still odd, right? And what about this number? This is an even number. So what about powers of even numbers?
They're
It's
even.
Even. Okay, so now we have an interesting equation here. An even number plus an odd number equals an even number.
Well, but
What do you think about that?
I don't know,
but like 2 plus 3 is an even plus an odd, but that's an odd.
Ah, so it looks like even plus odd is
odd.
always odd. Huh, so how could this work? That's odd.
Yeah.
That's odd. So let's see, can an even number plus an odd number ever be an even number?
Does it have to be integers?
Yes, all integers.
Well, I don't think so.
I don't think so either, because an even number means it's divisible by 2, right?
Yeah.
This means it's not divisible by 2.
Yeah.
So can a number that's divisible by 2 plus a number that's not divisible by 2 be something divisible by 2?
No.
No. So this equation must be wrong. Okay, so it turns out that the Simpsons were wrong. And one of the smartest mathematicians who ever lived,
Is it right?
he got it right. This one's a little harder to see just because you can't do it just with evens and odds, because this is odd, odd, even, and an odd plus an odd can be an even.
Yeah.
And even if you did your last digit trick, this is the last digit of 7 to the 12th, this is 1. Because the powers of 7 go, they
7,
go around in a
9.
circle. They go 7, 9, 3, 1,
Yes.
7, 9, 3, 1. So this is 1, 5, and the last digit of this is a 6. So even on the last digit, this one works. That one's a little harder, but this also turns out not to work. Pretty neat, right?
Yeah.
Yeah.
So this was Fermat's last theorem was one of the most difficult math problems that's ever been solved. It took over 350 years for somebody to solve that.
Whoa.
So don't ever complain to me that your homework's taking too long, because that took 350 years. Would you like to work on that?
It's already solved.
Oh, good point. Well, okay. Good job, guys. Maybe next week we'll talk about another famous unsolved problem.
Alright.
All right. Good job, guys.